peak of the class. All right, today's part 2, last part of probabilistically checkable proofs. So I know that was an eternity ago, so let me remind you the high-level ideas were. So, wow, we did a lot, haven't we? Okay, so, so we know the difference between P and NP. P means there's polynomial time algorithms, NP means that you can verify a solution in polynomial time. And so we're looking at an extended definition of sort of randomized provers and randomized verifiers. So something is in PCPRQ, where R is for number of random bits and Q is a number of queries. If you're trying to decide if something X is in the language that you're thinking about, and you're given Oracle access to a proof Y, and you're basically allowed to flip R random bits and make Q queries. Okay, so maybe you're trying to verify if a stat formula is satisfiable. The proof is the assignment. But what you're going to do is instead of checking all the clauses, you might randomly sample a few clauses to check or something. Okay. And the rules are, if X is part of your language, if you're supposed to say yes, then no matter the proof, you should always be saying yes. Okay. If X is not valid, if X is supposed to be rejected, then you should reject X sometimes for any Y. Okay. All right, so this is particularly interesting if we limit Q to be very small, like a constant. Okay, so can you with any confidence reject something that should be rejected, only looking at a few bits of the proof? Okay, so I did have it backwards, by the way, last time, although they're still small numbers. Okay, so the PCP theorem says that MP is actually equal to PCP log n01, meaning I can flip logarithmically many random bits and just make a constant number of queries, okay, and then reject something with some constant probability. Okay, so that's a very strong statement, a very interesting statement. It's saying kind of anything that has proofs, right? Anything that can be supported by proof, not only has a proof, but has some kind of like very robust, easy to sample format of a proof. Okay, so for SAT, that might be much more or somewhat more complicated than just the satisfying assignment, because it needs to be some kind of robust proof so that I can randomly look at just a few bits of the proof and still decide with some confidence that this formula is unsatisfiable. Okay, so part of the strength of the statement is that the class of NP is very big. There's all problems that can be verified in polynomial time. It's saying that all problems that can be verified in polynomial time can actually be verified with like a constant number of random bits being read from a proof. Okay, the format of the proof may change, although it can't change too much. It still needs to be polynomial size. Okay, but nonetheless, there's some way to have these robust proofs. Okay, so that already is a very kind of interesting, deep idea because it, at some level, enhances the meaning of proofs. Right? Not only do there exist proofs, but there exists sort of very redundant or robust proofs. Okay, so it leads to very maybe more concrete or practical terms, inapproximability results such as the fact that you can't do better than 7/8 approximation for 3 stat, and 7/8 is the easiest thing that we did on lecture 1. Okay. So maybe we take it for granted now, but that's really a bold statement to claim. Okay. Of course, we won't be able to get all the way to 7/8, but we'll still get some constant by the end of class. Okay. All right. So one direction is kind of easy, and I think it's sort of in the homework, which is so that PCP is a subset of NP. If you have some kind of probabilistic verifier, then you can get a polynomial time verifier. Okay. So the hard part that we're interested in is trying to take a problem in NP and construct some kind of PCP for it. And the problem we start with is just three colorability. Can you color a graph in three colors? Okay, and this is an example of a constraint satisfaction problem. So this is just something more general than SAT, but we have some variables V and an alphabet A, and you're going to assign letters to variables. Okay, and then you have a bunch of clauses. Each one takes, say, some Q variables. So it takes as input Q letters and either accepts it or it doesn't. There's some set corresponding to the clause. Okay, and that's all. And we generally focus the most, oh yeah, just some notation, unsat P, that's the minimum fraction of unsatisfied clauses. Okay. And what we started showing last time, or started to work on, is trying to prove this thing, which is that CSP is NP hard to decide if it's completely satisfiable or if at most half the clauses can be satisfied. Okay, so there's this whole gap that you can skip over. If it was 0.25 or something, you can answer yes or no, and that's fine. But there's this whole gap there. Okay, so all right, we did that last time. Now we started doing a lot of graph constructions. So two area CSP is when every clause is only two variables, which we can think of as a graph. So the variables are now vertices. Each clause between two variables can be thought of as an edge. Okay, but of course we could have many clauses involving the same two variables. So this can be a multi-edge graph. Okay. So graph coloring is such an example. Okay, so for starters, just starting from graph coloring, since 1 over m is the minimum possible non-zero unsat, we know it's NP hard to distinguish between unsat being 0 and unsat being 1 over m. Okay? And now our goal is to take 1 over m and try to ramp it up to a constant. I don't think we'll get to 1/2, but we'll get to some constant, which already is a pretty good proof of concept. Okay, so how do we do this? So we do something that's actually similar to the two lectures before our last one. So in those lectures, we're doing things like deterministic connectivity and trying to kind of reduce randomization by walking in expanders. So this too, we're going to sort of take a graph CSP problem and do a bunch of graph transformations. Although we also have to adjust the corresponding constraints at the same time. So it's more than just a graph transformation. Okay, but it's building a lot of graph ideas and gradually try to ramp up unsat by a little bit, say like double unsat with each iteration without increasing the size of the graph by too much. Okay. All right, so then basically 1 over m becomes equivalent to whatever constant we end up with, because you can just layer and build up and build up and build up until you reach some threshold. Okay. All right, so we did the first step and we introduced the second step. The first step is a pre-processing step where we just make G a constant degree expander. I actually only presented half of this last time, and that's why I was slightly confused. Okay, so in general, you're given a graph CSP. It may be very uneven. It may be a kind of a messy graph. We don't assume anything about the graph. And this will be more helpful in the next step. I want to do two things. I want to make sure A, the graph is constant degree, and B, that it's an expander that has constant spectral gap, that random walks mix quickly. Okay. So the first step to reduce the degree was to take each vertex and kind of split it into one vertex for every edge. Okay. So now everyone basically has degree 1. But the problem is that sort of one vertex became a cloud of vertices, and they're not actually required to be equal to each other, which we would want from the original problem. Okay. So we add a few edges in between to force equality. You can add, for example, a constant degree expander, which sort of has strong connectivity but doesn't add too many edges. Is the key point. So overall, the graph is still sparse. Okay. All right, so you just kind of blow up each vertex and adds a sparse set of equality constraints so that each cloud, everyone still needs to be equal. Okay, and then you can show that, okay, I don't increase the number of edges too much. The graph is a constant degree graph and it's regular. And the unsat doesn't change by very much either. This is not too hard to show. Okay, but it doesn't address the part about making the graph an expander. Okay, how do we make the graph an expander? It's actually a very simple trick. This is what I forgot to present last time. Okay, so let's say that we have this graph or something, which is not a very good expander. It's a cycle. It takes a long time to walk around. Okay, and then we'll introduce an expander over the same set of vertices. This is not actually an expander, but it's supposed to represent like a relatively well-connected graph. And it should be sparse. There's not enough vertices to really draw a compelling sparse expander, but that's okay. But the point is this graph is well-connected. Random walk in here should mix pretty quickly. This graph isn't. If I threw them on top of each other, random walks will still mix pretty well, right? You still get a lot of connectivity from here. And then, okay, some of this is a little bit of a distraction, but that's kind of okay. So you can just analyze it and show, okay, sort of the spectral gap will sort of be the average or some combination of these two spectral gaps. And so at least be some constant times this. So you'll get a constant over here. Okay, so you just throw one expander on top of the other. And then we'll just add like trivial, okay, this is a graph. We need to give them constraints. But really the constraints shouldn't matter. So we'll add like trivial constraints, like any letters will satisfy that edge. Okay, so that would make an expander graph CSP. Okay, so that's how you address the spectral gap. So now going into the second step, I can assume that G is a constant degree expander. And I guess the really interesting part is, oh, why do we need a constant degree expander? That's what we should keep an eye out as we do the more interesting parts. Okay. All right, so we went a little bit over the intuition. So this is really the main step where I try to ramp up the unsatisfiability of G. And so the thought experiment was, well, okay, if I independently sampled like 10 edges from G and I made that into a one big constraint, right? Now I've gone from 2 variables to like 20 variables because there's 10 edges, 2 variables each. Okay, so that's fine. Now this big bundle of edges, this bundled constraint, can only be satisfied if all 10 were satisfied originally. So it's kind of harder to satisfy each of these things. Okay. So if I was getting 10% of them wrong originally, then the bundles have each randomly sampled bundle has a much higher than 10% chance. I don't know, 50%, 30% or something of being unsatisfied, right? It just ramping up by repetition. Okay. All right. So, okay. So the unsat will improve. That's good. Now there's 2 drawbacks. One is the number of constraints goes up by a lot. Okay. So if I was doing bundles of T, then I'll go from M constraints to M to the T or so constraints because every choice of T. Okay. We do want to be mindful, because PCP, this overall proof, the problem sizes need to stay somewhat similar, right? Because the proof still needs to be polynomial size and stuff like that. So I can't just blow up things willy-nilly without paying any attention. So M to the T, I want to be a little bit careful about. Like I couldn't just set T to be log n or something there because that'll take my polynomial many constraints and make it, more than polynomial. Okay. And another issue is that this is not a graph CSP anymore because there's, 2 T variables involved in every constraint. Okay. And the graph stuff is really important for us to be able to do all this machinery. That's really why we're doing the graph, is because we have these strong graph properties, like we understand expansion, we understand regularity, stuff like that. And somehow that lets us do a lot of interesting, unusual things. Okay, so we've sort of had this idea before. The analog of independent sampling is to take random walks. Okay, so instead of doing bundles of 10 completely random edges, we'll do a random walk of length 10, and we'll just bundle up those edges. Okay, And the high-level intuition in this and many preceding lectures, if the graph is an expander, so it mixes very well, then a random walk behaves kind of like an independent sample. Okay? So somehow when we take a random walk in a low-degree expander, there's actually not that many different random walks. There's only a few choices in each step, and yet you're sort of getting the power of an independent sample. You know, it's not exactly the same, so we always have some like calculations and some dependency on gamma that's shown up time and time again, but that gamma is usually a constant, and so, okay, it's a little bit more notation, but otherwise we can deal with it. Okay, so that's the intuition. Let me remind you what exactly the construction was. So in general, for some parameter t, I want to take all the t-step walks. One thing slightly different than before, for technical reasons, we're going to take t-step lazy walks. That means each step I flip a coin. If heads, I'll take a real step. If tails, I'll just stay right there. Okay. So you end up taking roughly t over 2 real steps, but it could be a little more, it could be a little less. Okay. All right. So for every one of these t-step lazy walks, that'll become an edge in g to the t. Okay. And okay, so now I want to roughly take t edges on a path or a walk and bundle them into one constraint. Okay, but I also kind of want to produce a graph CSP at the end. So whereas originally there's kind of 2 t variables involved, I want to make that look like just 2 variables. Okay, so what we kind of do is we increase the alphabet size by a lot. Okay, so that the endpoints, each variable will have so many letters, you can think of it as this variable assigning a letter to each of its neighbors and roughly nearby vertices. Okay, so that when I'm looking at a t-step walk, the endpoints will be assigning a letter to roughly every, or to exactly to every vertex along the way. Okay, so capital D is a number of total vertices within t steps of a vertex, or an upper bound. Okay, it's roughly 1 plus d to the t, apparently. Okay, and instead of just assigning one letter to a vertex, I'm going to assign capital D letters to each vertex. Okay, and the way to interpret this is that, okay, so a label on a vertex now has, you know, a ton of letters. But I'm going to think of that as one letter for each vertex in this t-step neighborhood. Okay, so I can think of each vertex as assigning a letter to each of its nearby vertices. Okay. All right, so now with that kind of letters, so given one of these walks, we're going to create a constraint in that powered graph if it's satisfied by the following. If I look at the labels that one endpoint is assigning to all the vertices along the walk, okay, that should satisfy all the edges along the walk. All the real edges, the self loops from the lazy part you just skip over and ignore. Same with the other endpoint. If I look at sort of that local labeling from the opposite endpoint and how it labels all the neighbors, it should satisfy all the edges in between. And then lastly, these two should be agreeing on all the vertices in there that they have in common. Okay. All right, so blowing up the alphabet size is not great. We'll have to address that in the next step later. But otherwise, we have roughly done, you know, sort of the analog of taking the t power of a graph. We kept it a graph CSP, and we're able to sort of make a constraint for every t-step walk in the graph. And we hope to show in the analysis it's going to behave like a t-step or independent sample of t constraints, and that will get some amplification. Okay? The cost we paid was the alphabet size going up, you know, sort of exponentially in D. Okay. All right, so I think that roughly gets us caught up to where we left off at the end of class. Okay. I guess I drew a picture, but it's not very useful. All right, so here's now what we're going to try to show. In this powered graph CSP, which I'm calling G to the T, The unsat has gone up by basically a factor of square root t. So t is going to be a constant. So if unsat g is already bigger than 1 over t, then we're done. We've already shown that it's bigger than a constant, and I'm happy. Okay, so you can sort of ignore the min part and just focus on unsat g, in which case we're really going to show that unsat g to the t is greater than roughly square root of t times unsat of g. Okay, that's the hard part. All right, okay. Okay. Well, I guess I left us a rhetorical question. Maybe it's a good chance to wake up because I've been ranting for a while. How can we try to set up a proof? Like, how might I try to go about proving this? All right, here's what we'll do. Okay, so we'll start with an optimal label for g to the t. Okay, I'm going to call that pi bar. Okay, and from pi bar, I'm going to extract some kind of label for the original g. Okay, and I guess I want to show that if the derived label pi makes a lot of mistakes, then pi bar must make a lot of mistakes as well, or a square root t factor greater. Okay. All right. Okay. So how do we derive this thing? Okay. So we're assuming that pi bar is an optimal labeling for the powered graph. Okay. And so how are we going to define pi? Pi will be the labels for the original graph. Okay. All right. For each vertex v, imagine taking a lazy random walk, say for t over 2 steps. Okay. You're going to land somewhere. And that vertex, based on pi bar, would have said, oh, I think my starting point's label is A or B or C. Okay, so I take a random walk and I look at what that person thinks of where I started. That's some random letter. Okay. We're going to find pi V to be sort of the most likely letter to come out of this random walk. Okay, so it's some kind of like a weighted vote. You're taking a vote of all the neighbors to think, oh, what do you think my label is? Okay, and the winner of the vote is what pi v becomes. Okay, the weighting of the vote is sort of based on who is most likely to be where you stop on a t over 2 step lazy random walk. Okay, but I guess just because pi v is the most common letter to appear from this random experiment, we know for starters that the probability that pi v is equal to, you take a random walk, land somewhere, and see what the letter is at least, 1 over the size of the alphabet. Because somebody has to be at least 1 over the size of the alphabet. Whatever's the most common. And as far as we're concerned, that's a constant. So the alphabet coming into this is a constant. The original graph 3 coloring, A was 3. Okay. And in further iterations, we'll get the alphabet size back down. Okay. Now, okay. All right, okay, so what we want to show is that for every mistake that pi makes, pi bar should be making like square root t or so mistakes. Okay. Now, originally I wanted to just do unsat of GT and unsat of G. So I'll point out that pi bar was supposed to be optimal. So this is the true unsat of GT. Okay, so here I'm kind of writing, what's the unsatisfiability of pi bar in GT is what I mean by this notation. Okay. All right, so this is equal to unsat GT, which at least square root T times, unsat, how many mistakes or a fraction of mistakes pi makes in G. And pi is not even necessarily the best solution for G. So the true unsat of G might be even smaller, which is fine. Okay. So that'll be greater than equal to unsat of just G, whatever is the minimum pi. And so you get the original thing that we wanted. Okay. All right, so I want to show that every mistake in G that pi makes in G roughly corresponds to square root T mistakes in the powered graph. Okay. We need two lemmas. Okay. Both somewhat technical, and both there's some homework exercise to actually force you to double check the real details. So I'm going to focus just on the high level ideas here and then get to the more what I feel are the fun parts. Okay, so we're going to let capital I be the set of all indices that are very close to T over 2. So within square root T over 2 of T over 2. Okay, roughly a standard deviation away from the middle. Okay. Now, before we pointed out that, the odds of a random walk of lazy walk of T over 2 steps getting the same label as pi v is at least 1 over the size of the alphabet, which is at least a constant. And what we're doing now is we're going to extend that to all I close enough to T over 2. Okay. So if I start at V and I walk around for I steps where I may not be exactly T over 2, but it's pretty close to T over 2. Okay. The odds of wherever I land being that popular opinion of V will also be at least a constant. That's the claim. All right. Okay, so just kind of making that first statement a little bit more robust to allow a little flexibility in I, sort of up to a square root T kind of window. This is really where why we do a lazy random walk, it's where it's going to come in. Okay. Does anyone want to try to guess the intuition behind the proof? You want to use the fact that it's a lazy random walk. Also, please ask if the claim makes sense, because there's a lot of intuition coming really fast. Or a lot of notation coming really fast. So I know if I take T over 2 lazy random steps, I have a good chance of getting that popular letter, because the popular letter is whatever's the most popular among T over 2 steps. But what about T over 2 plus 1? I take T over 2 plus 1 steps and I look at what label it gives to V. The claim is that should also be, maybe not exactly 1 over size of A, but still should be a constant. But what's the idea? Yeah, that sounds like a random guess. Well, I think we could try to approach this on slightly simpler terms in any case. It might come back to what you're describing. Okay, so let's just say that what's the difference between t over 2 lazy random steps and t over 2 plus 1 lazy random steps? Come on, you guys know the difference. Okay. What's the difference between t over 2 random steps and lazy random steps and t over 2 plus 1 lazy random steps? One lazy random step. Okay, good. That we feel good about, right? All right, so you take t over 2 steps and then you flip one more coin to decide whether or not to take one more step. If you get tails, it was really just a t over 2 step, right? So like half the time, it's going to be acting like a t over 2 lazy random walk. There's some correlation between t over 2 and t over t2 plus 1 because that's just one more coin toss. Okay, so what's an alternative way to sort of generate? Okay, so one way to do a lazy random walk is to toss a coin every time you're about to take a step, right? But we can also toss the coins ahead of time, okay? So let's say j sub I is sort of how many non-lazy steps you end up taking out of I steps, okay? But that's sort of like, oh, out of I coin tosses, how many came up heads, right? So I can flip it first, okay? And then take the appropriate number of real steps in the graph, okay? Now, flipping 1 million coins and seeing how many heads and 1,000,001 coins and seeing how many heads is not that different. It's pretty similar, okay? And in general, okay, maybe square root t seems like a lot, except if t is really big, square root t is small, right? Square root t is smaller than any constant fraction of t, okay? So this is small enough that, all of these I and I are so close to t over 2 that ji is going to be distributed really similarly over all I and I. So if I sort of just, drew the distributions, it'll look like a Gaussian because it's, sum of coin tosses, right? They're going to be highly overlapping. So you can see here that the probabilities are very close. And you can work your way through the actual binomial distribution and verify this. Okay. Now, all that really matters is this number j, right? So once you know j, then you just take j real steps and you look at the label. Okay. So if you knew j, then I no longer matters. Right? So conditional on j. Oops, rats. Conditional on j, this sort of destination label is independent of I. Okay. So really all that matters is j, and a distribution of j's is really similar for all I and I. Okay, you put those two facts together, do a little bit of math, okay, and you'll get the result. So the homework will basically ask you to flesh that out, but that's the high level idea. Okay, but that's also partly why we do lazy random walks. Okay, is because it sort of lets us expand from just t over 2 to roughly an interval with square root t around t over 2, and we'll see why that's useful. Okay. All right, so that's one lemma. Again, a little more technical. Haven't done the fun part yet. Here's another sort of technical lemma that we'll use, and of course I'll have it on the right hand side when we do use it. So this one we're not going to do a proof because actually it's very similar to some stuff we had done previously in terms of like random walks, escaping bad sets, and stuff like that. Okay, so in general, if a random walk looked like an independent sample, okay, so let's say that I have a bad set F. Let's call this shaded region F. Okay, and I'm sort of interested in how often I'm in F. That was sort of the case with some previous lectures as well. So what this statement is actually interested in is if I randomly sample like one endpoint of one random edge in F. So I pick a random edge in the shaded region, and then I pick one random endpoint, and I took a random walk for, I don't know, 5 steps. Oops. So I take a few steps of a random walk. What are the odds that 5 steps later I'm still in F? Okay. So if it was a completely independent sample, then it shouldn't matter that you started in F. Like each time is a completely independent sample. But it isn't quite independent. Okay. So, all right. So V0, V1, V2 is some random walk. Where V0 is a random endpoint, a random edge in F. And this is saying, okay, what are the odds that roughly, I think this is the I plus 1th edge. So the step from VI to VI plus 1, what are the odds that that is still in F? Okay. And the lemma says it's at most the proportion of F, that's mu, plus something decaying in the spectral gap. Okay. So mu is what you would get if it was a completely independent sample, right? So in every time, oh, chance of mu, if there was no correlation between steps. So you have this error term, 1 minus gamma to the I, but it's decaying, especially if gamma is a constant. Okay, so there is some error term. It's not an independent sample, but it goes to 0 very rapidly in an expander graph. Okay, this is very similar to, for example, what we did, I guess, 2 weeks ago when we were talking about how to reduce randomization. And there was sort of this bad region of samples that we were trying to escape. And it was like, oh, what are the odds of escaping and stuff like that. And you'll see the proof is sort of similar. And that's why I've tried to leave some of it as an exercise. Okay. All right. So this is similar to something we've done before, and something that is also kind of easy to package as a black box for what I feel is the more interesting parts of the proof. Does this statement make sense now? Okay. All right. All right. Now let's get back to trying to show this thing. Roughly, for every mistake that pi makes on G, we should get square root T mistakes that pi bar makes in G to the T. Okay. All right. So let's see what's here. All right. So I'm going to start setting up some notation. Okay. So F is going to be sort of the bad edges. Okay. F will be the edges that are failed by our artificial labeling pi. Pi is sort of that most popular neighborhood labeling thing derived from pi bar. And we're going to assume that mu is at most 1 over t, which is really the interesting case anyway, because if unsat was already bigger than 1 over t, we're essentially done. But for, if you're worried about technical things, we can take F and just drop a few edges from F until mu becomes less than 1 over t. And that would be okay for the rest of the proof. Okay, but just think of mu as smaller than 1 over t. Okay. All right, so let's see what comes next. Okay. All right, so let's look at a random edge in G to the T, which corresponds to a uniformly random T-step walk in G to the T. Okay. There's different ways to sample such a thing, but anyway, this will correspond to also a uniformly random edge in our G to the T. Okay. And I'll let E sub I denote the ith edge in this randomly sampled walk. Lazy random walk. Good. All right, so we're going to set up some indicator variables. Okay. So we're really just going to look at the middle square root t or so edges on the walk and focus on them, kind of discarding all the other ones, even though technically those would have to be satisfied too to satisfy something in G to the T. In the analysis, we'll just ignore it. That's okay. We're being conservative. Okay. So for each of these indices that are close to the middle, okay, we're going to say xi equals to 1 if, okay, the labels are sort of agreeing in a sense that V0 assigns to VI minus 1, the kind of popular label for VI minus 1. And VT is assigning the popular label to VI. Okay, so if sort of you have some agreement between the local labeling and the derived labeling for that particular edge in the middle, okay, and pi fails the constraint. Okay. All right, so that's going to be our random variables. Maybe it'll be good to motivate it. So I think that's coming up. Okay, so all right, so why do we set up these random variables? Let's let x be the sum, okay, of I and I xi, okay, the sum of these random variables. Okay, so okay, so what happens if okay, so let's look at the okay, so this walk corresponds to an edge in g to the t, right? So let's say that x is at least is something non-zero. So one of those xi's turned out to be 1. Okay. So if one of those xi's turn out to be 1, what does that say about the corresponding edge in g to the t and whether or not we either satisfy or don't satisfy it? Because we've got a lot going on in the right-hand side. Sorry? Okay, so let's say that some xi is equal to 1, say xt over 2 or something, right? Okay, so that means that if I looked at that edge, then we have these conditions that v0, uh, what v0 thinks that vi minus 1 is, agrees with pi v0, and what vt thinks that vi um, is equal to pi v0. And those two don't actually satisfy that edge. Okay, so that's one of the ways to not satisfy that whole walk. Yeah, so okay, so if x is bigger than 0, then that means that for that walk, then that means that walk is not satisfied in g to the t. Now, if x is a uniformly random walk or a uniformly random edge in g to the t, then the probability that x is greater than 0 is a lower bound on unsat g to the t. Okay. So, because we're just looking at a limited set of conditions that would violate an edge. The actual conditions are more strict. Okay. So now we need to analyze this. This is where things will, the analysis will become a little bit more conventional because we're looking at sums of indicator variables and the kind of stuff we like to do. Okay. Interesting. Okay, so fine. Okay, so well, maybe we should also zoom into the construction of the powered graph, right? So pi bar is for each vertex sort of giving a labeling to the entire neighborhood of that vertex, entire neighborhood of that vertex. And when I look at a walk between two vertices, okay, it's only going to satisfy that walk if when I look at this guy's labeling for the whole neighborhood, it satisfies every edge on the walk. And when I look at this labeling for the whole neighborhood, it satisfies every edge on the walk. And when I look at anything overlapping their neighborhoods, they agree. Okay. So they have to agree on everything on the path, on the walk, and they have to get the whole walk correct. Okay. And now when I'm looking at these conditions here, I'm actually not necessarily forcing them to agree. Why is it, sorry? Oh, it's arbitrary. It's arbitrary. I think part of it is just because, at some level, there is some gap here, right? I just want to do something more conservative and say, oh, these conditions are enough to imply that the constraint wasn't satisfied, but it's simple enough that I can analyze. Yeah. Um, yeah. So it's arbitrary. Yeah. We were allowed to do, simpler things that are more conservative, that are good enough for the proof. And by keeping it simple, it'll be easier to now start analyzing the x's and what it means. Okay. All right. My guess is, we'll kind of go through the proof together, but I do think it's a bit much to like take the whole thing and understand everything that happened in one pass. But hopefully, the ideas will be there that you can go back and check the details again and see how it all comes together. There's only so much we can do, kind of, in one class. So, all right. Okay, so we're going to start analyzing the xi's, and we're going to start with the expected value of xi. Okay. So, okay, so mu is basically unsat of G. Okay, number of bad edges. And so I want to argue that the probability that xi is equal to 1 is roughly the odds of a bad edge, of sampling a bad edge. Does that make sense? Okay. So here's what we do. So all this is based on a uniformly random, sampled random walk in G. Okay. So what we're going to do is we're going to generate the random walk maybe in a different way. Okay. This would also work. Suppose I sample the ith edge first. So I choose vi minus 1 and vi first, including also the direction. So you choose the edge and you choose the orientation randomly. Okay. So I'll choose that middle edge that I'm analyzing right now first, and then I'll sort of figure out the random walk backwards and the random walk forwards. Okay. Because G is a regular graph, you can double check that this will still generate a uniformly random walk, lazy random walk in the graph. Okay. So so you can actually just start from the middle and then randomly walk outwards, and then you get a t-step lazy random walk, uniformly random. But the obvious convenience is that, okay, E sub I is now in the middle, and that's kind of, independent of the other steps. It comes first. That's going to help us in the analysis. Okay. So, so the probability that xi is equal to 1. So first of all, we need to choose it needs to be a bad edge for xi to be equal to 1. It needs to be one of the edges that pi fails. Okay. So, and then, did I do it right? Okay. All right. So, right, there's the definition of our random variables. So A, I need to sample EI to be one of the bad edges. And then I need to walk, to V0 and say, okay, what are the odds that V0 assigns to VI minus 1 the same as that should be VI minus 1. Okay. And what are the odds that when I walked from VI to VT, I arrived at something that assigns the same label, the popular label, to VI? Okay. So does this part of the statement make some sense. So I have to sample EI to be a bad edge, okay, because that's condition 2. And then I need to check condition A. Okay, if I walk back to V0 and if I walk forward to VT, are they going to agree with pi for those endpoints? All right. Now, what are these two? They're definitely less than 1. Yes. They're also greater than 0. At least greater than or equal to 0. Great. We're at the second last week of the year and we've established that. Yeah. Yes. Now you tell me. So if this was less than equal to 1, which I agree with, or if anyone disagrees, let me know, then we would conclude that this is less than equal to mu, which would be an upper bound. You want lower bounds, that means you want a lower bound for each of those probabilities. Okay, but why? Oh, okay. So we have this lemma. Okay. So if I was like a t over 2, then going to V0 would be a t over 2 step random walk, and it has a good chance of being the popular label because that's how the popular label was defined. But the lemma says that also for steps I that are close enough to t over 2, within square root t or so, the distribution is similar enough that the probabilities are within a constant factor of each other, and in particular, at least a constant overall. So we apply this lemma that we kind of briefly went through earlier to these. So those are both at least a constant, and you get some constant times mu. Okay. All right. So that's the first claim. The next claim is to show that the expected value of x squared is at most square root t times mu. Okay. All right. So this will expand into a big sum, which will have a lot of cross terms. So we have one more baby claim first, okay, which is that if I look at two of these things, we have some bound on the cross terms, right? So remember, x is the sum of xi's. So when we expand out x squared, we're going to get a lot of these xi, xj terms. That's why we're dealing with it now, and then we'll come back to the x squared. Okay. So let me tee this up for you guys. So we're going to simplify this a little bit, okay? And I'm going to let define yi to be 1 if ei is one of the bad edges, and 0 otherwise. Okay? So xi requires ei to be bad and also the labels to match and stuff, right? So xi is more strict than yi, so xi is always less than equal to yi. Okay, but yi is clearly simpler. So, okay. All right, so expected value of xi, xj is at most expected value of yi, yj. And now I'm going to do some conditional stuff. Expected value of yi times the expected value of yj given yi is equal to 1. So think of j as being bigger than I. Doesn't matter, but you can just choose one and fix it. Okay. So expected value of yi, what does this represent? Yeah, the probability that the I step is the bad edge, right? And if you want, we can sample the random walk like before, where we sample the ith edge first and then do the rest of the walk, right? Okay, so the ith edge is bad. So what are the odds that the ith edge is bad? Mu. Okay, good. Perfect. All right. What are the odds that the j step is bad, given that the I step was bad? Yeah, okay, so why can I use that lemma? Yeah. So if we think of the generated random sample by starting with the ith edge, so I choose a random ith edge and then a random orientation, then I'm really choosing a random endpoint of a random edge in F. I mean, if I'm conditional on yi equal to 1. And then I want to know whether yj, which is like j minus I steps later, is also going to be in F. So that's exactly the format of the lemma from before. Okay. So that will correspond to this lemma, okay? And then you'll get this like mu plus 1 minus gamma j minus I minus 1 kind of thing. There's a minus 1, but it doesn't matter too much. Okay, and you multiply that together, you'll get that claim. Okay, so the claim looks a lot like that lemma for that reason. Okay, so we have that, and we can finish. I think we're actually going to finish in this class. That's awesome. Okay, so now let's analyze this thing. Okay, so the expected value of x squared, breaks out into something like that, right? Nothing special. Now, okay, I can apply our first claim to expected value of xi, so that's at least mu or something, and there's 1 for every index in I. Okay, so this is at most mu times the number of indices. That's like square root t or so, right? And now, okay, if I plug in the one we just did for each of these cross terms, okay, so you get a mu squared times every pair of indices. So that's like 2 mu squared, number of indices squared. Okay, and then you get this mu times 1 minus gamma thing. So 2 times mu times over all these indices, 1 minus gamma j minus I minus 1 kind of thing. Okay. All right, how do I upper bound this? Okay, so if I fix I, the first edge, and then I go over all the different j's, you get like 1 minus gamma plus 1 minus gamma squared plus 1 minus gamma cubed plus 1 minus gamma to the fourth and so forth, where gamma is some constant. Think of it as like 1/2, right? So what does that all add up to for one fixed I? Sorry? Yeah, it's geometric series, so it all adds up to a constant. I mean, if gamma is a constant, otherwise it's like 1 over gamma or something, but gamma is a constant because we're in an expander graph, so that's important. And then there's, I choices. I mean, there's, one I, there's square root t choices of I. Okay. So we get something like big O mu size of I plus mu squared size of I squared. Okay. And this thing is like t because I is about square root t. Okay. And mu is at most 1 over t. So I can take 1 mu to annihilate 2 mu I squares and stuff like that. So really the dominant term is mu times the number of indices. That's mu times square root of t. Okay. All right. So that brings us to what we originally wanted to prove, which is lower bounding the probability that x is greater than 0. So the first thing we do is we analyze the expected value of x. So this just applies that first claim, and linearity of expectation, and the expected value of x is going to be at least square root t times mu or so. So the next step is to evaluate expected value of x squared. So here, we're first going to take conditional probabilities, the expected value of x, given x is greater than 0 squared times the probability that x is greater than 0 squared. So in the bottom right here, I have Jensen's inequality. So for the function f of x is equal to x squared, this gives us at most the expected value of x squared. Again, conditional under x greater than 0, that's totally fine, times the probability that x is greater than 0 squared. And I'm going to, sorry, that shouldn't be there. So now I'm going to put one of these probability of x greater than 0 back in and remove the condition. And I get the expected value of x squared times the probability that x is greater than 0. Okay. Good. And now, rearranging, we get that the probability that x is greater than 0 is at least the expected value of x squared divided by, the expected value of x squared divided by the expected value of x squared. And this is going to be at least, some t times mu squared divided by square root t times mu. So this will give us square root t. Let me do it down below. This will give us square root t mu as desired. Okay, good. So that covers that. And now we move on to the next steps. Okay, so let me explain the alphabet reduction step, because this is also conceptually kind of interesting. All right, so we made the graph a constant, degree expander. That was very helpful and empowering because it limits the number of constraints I make. It also kind of limits how much the alphabet blows up by, because I take a t-step random walk and I want to do the whole neighborhood of t steps, and that's going to change the alphabet from size 10 to 10 to the d to the t or something. But that d is playing a big role. Okay, so the fact that d is small is very useful. Okay, all right. All right, so let me explain alphabet reduction and we'll get out of here. All right, so the goal is to take my moderately large alphabet size and reduce it to a constant. All right, so, okay, so step one, which I think is maybe coming out of nowhere, is that, and I'll explain in a moment, I'm going to take that moderately large alphabet and reduce it to just 2 letters, 0 or 1, okay, by introducing error correcting codes, right, blast from the past. Okay. Now the cost is that we're roughly going to take a single edge, between 2 variables and sort of blow each variable up into many bits and have like a constraint that's now involving many bits. So it's not just an edge anymore, okay? You have a more general formula over many variables. Step 2, okay, is to figure out how to take these complex constraints, somewhat more complex, there's no longer a graph CSP, and take each one of them and replace it with a graph, okay? I'm just going to explain that part as a black box. We don't have the techniques to analyze it. That was the goal of next lecture, okay? All right, but roughly, the error correcting code is going to blow something up, and then we have to bring it back to a graph, okay? So let me explain this part, because it's kind of interesting. So I think one thing that's sort of conceptually interesting, if you just take a step back and abstract out some of the technical details and stuff, is that, what we're proving at the end of the day, okay, there's no difference between non-zero unsat, satisfiable or not, and some constant error, which is a pretty strong statement, like very strong kind of, tolerance for approximation is a very big, bold qualitative thing. And the ingredients that are going into this is like random walks on expanders and like error correcting codes. And then the part that I'm omitting has to do with some Fourier analytic techniques, which we'll quickly survey next class, right? But it's quite the kitchen sink of funny techniques. I mean, odd techniques, right? Calling on different parts of our class to do something pretty profound. So, okay. All right, so I drew like a triangle with 3 constraints just for illustrative purposes. Of course, there's more constraints and more edges out there. But the first step is we make some kind of error correcting code. Okay. So from my alphabet to 0, 1 to the L, okay, where L should have size logarithmic in the size of the alphabet. Okay. So that with some, constant relative distance. Okay. And that will follow from our error correcting code lecture from a long time ago. Okay. So that means that if I have any two kind of words that aren't the same, and I look at the distance between the two code words, so the code words are going to be in some higher bit space, I want them to be kind of far apart, right, in general, so nearby things will be decoded correctly. All right, so I want it to be at least rho times L for some constant rho. Okay, L is the total number of bits, say 1/2, L over 2 or something. Okay. All right, so we're going to split each vertex into L vertices, where L matches that output length of the code. Okay. And now here's sort of so now each edge, the problem is that one variable has been split into L variables. Okay. So we're going to make a formula that takes all of those two L variables from U, L variables from V. Okay. So that's 2 L bits. Okay. And it's only going to output true if those 2 L bits, the first L bits represent some encoded A1, and the second L bits represent some encoded A2, and then those original things would have satisfied the formula. Okay, so we're using error correcting codes to roughly take a medium-sized alphabet to just bits. So the good thing is that there's only 2 letters right now. Okay? The bad thing is I don't have a graph CSP anymore. I have some formula that's roughly decoding along the way, or going through the error correcting code along the way. One thing I want to point out is that although this is kind of messy and L is somewhat moderate, the size L sort of depends on the size of A, which, while kind of big, is still some big constant, because we blew up a constant by a constant last time. Okay, so all of this stuff is constant size. It's kind of big, but it's not proportional to n. Okay, all right. So that's the first step. The next step is to replace each of these constraints, that are sort of going through the code, with a graph CSP. Okay, so this is why in the picture it's sort of like a graph now. Okay, so I originally had an edge between 2 variables. That became sort of a complicated constraint over L variables each, because that's using the code. Okay, and now what I'm going to do is I'm going to define a graph CSP where I'm going to keep those 2 L variables from before. It's going to add some more variables in the middle and then some edges. Okay, so it's roughly going to try to encode FE as a graph. Okay, but it's going to do something a little stronger. Okay, so the first 2 properties, it's going to include those variables that's been created for the 2 vertices. Okay, and the sizes are all going to be nice. Everything's going to be a constant because L was a constant, and whatever. You're looking at a constant size thing, something outcomes a constant. It is important to point out that we're going to have the same sizes for all the edges. Okay, so the construction will always create the same number of vertices and edges and stuff, because sort of what goes in is the same size. Okay, here are the 2 interesting properties. Property 1 is completeness. If in that formula, my bits for U and my bits for V satisfied the formula, so you can decode it and it satisfies and stuff like that, then you can extend, this assignment of bits to the rest of the vertices in that mini graph just for that formula so that the entire GE is satisfied. Okay, that's important because I want to make sure a satisfiable thing here is satisfiable there. Okay. The second property, okay, is soundness. It's a little bit involved. Okay, so suppose I have my bits for U and bits for V and they don't satisfy the constraint. So they're not representing some encoded letters that actually satisfy the constraint. Okay. Then for any way of extending and filling in those vertices in between, so any extension sigma of those 2L vertices, I should be unsatisfying some fraction that depends on the Hamming distance from any actual correct set of bits. Okay, so I'm taking the minimum overall, bits for U and V that actually satisfy the constraint. Okay, and looking at the distance from my bits to a correct set of bits, and it's relative out of, this should be 2L. Okay, so it's some fraction between 0 and 1 times some constant. Okay, so that means if my 2L bits are really far away from a correct solution, then I should be getting many of the constraints inside wrong. It should be proportional. Okay, so that's a little bit harder to get this kind of, because you're sort of preserving the error. Okay. All right, let's see if I have enough time. Okay, so this part maybe I'll skip, but it's not too hard. The most important case is when G was already satisfied, right? So if G was already satisfiable before I did all this crazy stuff, so I can assign the correct letters to U and V, and then I do the thing where I first blow it up with error correcting code, and then I sparsify it with this black box, then I can still satisfy everything here because for each of my two letters which satisfy the clause, I get the corresponding bits with the error correcting code here, and then there's some way to fill in everything in the middle to make everything correct. Okay, so satisfiability will still get me satisfiability. All right, what's more interesting is this step. This is very close to finishing. I'll probably go about 5 minutes over. Okay. All right, so I want to show that the unsatisfiability of G bar is bigger than the unsatisfiability of G. It's not too much smaller is really what it's saying. We may give back a little bit, but because what we're getting out of this is reducing the alphabet size to 2. Okay. All right, so let's see. Okay, so let's let pi bar be the optimum labeling in the output graph. Okay, and from that, I'm going to derive a labeling in the original graph G by using the error correcting code. Okay, so that's right. So for each vertex in the blown up graph, right, I have L bits. And I'm going to use the error correcting code to give me back some letter in the original graph. Okay, so we'll decode each of them. Okay, so the main claim is that for each edge E, if pi fails E, then I should be unsatisfying something proportional to that row, that distance between code words in the error correcting code. Okay, and if that's true, then since unsat of pi is going to be sort of the average of all the unsat pi of GEs, then you'll get exactly that. Okay, I'm going a little bit quickly. All right, so let's try to make this really quick. I know I'm over time. Be great to finish this though. Okay, so let's fix an edge E. Okay, and I'm going to let U bar sort of denote this whole bit string. Okay, and similarly for V bar. Okay. Okay, so now I know that okay, so pi U and pi V did not satisfy the constraint for E, right? This is what I know. Okay. Okay, and now, so at least one of those letters are wrong, right? I have to change at least one letter to get it right. Okay, and I know that the distance uh, between any two of the code words is like rho. The relative distance is rho. So if my bit strings goes to a wrong letter, to go to a right letter, I have to move at least like rho over 4 or something. Okay, so that means my distance from my wrong bit string to any right bit string has to be at least some constant times rho. Okay, so because the code words are far apart, okay, if the two letters are wrong, then the bit strings that decoded to those letters have to be pretty far from any bit string that's right. Something proportional to rho, maybe rho over 4. Okay, so because the error correcting code spreads out the code words, if the bit strings decode to something wrong, I would have to change many bits to get to some bit strings that are right. Okay, so the distance between my sets of bits from any correct set of bits is something proportional to rho. And finally, that crazy graph GE promises that if you're far away from a correct solution, you're going to get a lot of GE wrong. You're going to get something proportional to the distance. Okay, so that sums up that lemma. That's where error correcting codes comes in. Those are the 3 transformation steps. Okay, I know I'm going very quickly, and I'll fix the calculations in the notes. And just at the end of the day, when you put everything together, this will finish off our thing. Okay, so going in, I have no control over the degree or the spectral gap, and I have some unsatisfiability and some finite sized alphabet, constant sized alphabet. In the first step, we kind of overlay the expander. We make the degree small by blowing up everything. So at least the degrees are under control and I have some constant spectral gap. Okay. And then when I power, okay, the degrees go up, the alphabet goes up. That's really the important thing because it's easy to address the degree later. Okay. But the unsatisfiability really goes up by some factor times square root t. So all the betas are some constant. It could be smaller than 1, but we'll just make square root t bigger. Okay, we'll make square root t big enough. Okay, and at the end, in alphabet reduction, unsat may go down a little bit again, but because of the error correcting code stuff we just argued about, it won't go down. I mean, the amount it goes down is bounded by some beta 3 or something. So I guess some square root t times some constant times whatever I started with, and my alphabet size is back down to something very small. Okay, so basically we had the power, the alphabet went up, and then we fixed it with error correcting codes, and the Fourier thing I skipped. But at the end of the day, the unsatisfiability went up. And so you just can repeat this. You can verify the graph doesn't blow up too quickly. And that is somehow how you do it. Okay, so this just shows you how to get some constant with some calculations not quite correct, but still captures the main ideas. And I think maybe for me, the biggest takeaway is how many different ideas went into this proof. That to me is the most amazing part, is that you have all these ideas from completely unreal error correcting codes, Fourier analysis next time, random walks in a graph, the way they come together to give something very profound about computer science. That to me is almost the most exciting part. Okay, I'm way over. Thank you.